Hello everyone! In today's video, we're going to be discussing acidity. In this whole video, we'll be discussing acidity, the different ways we can measure acidity in terms of hydrogen ion concentrations and pH values, and how we can calculate the hydrogen ion concentrations and pH values of different acidic solutions, and how we can understand acidity in terms of these values. We are also going to be discussing a few questions regarding pH values and hydrogen ion concentrations. What is acidity? Acidity is expressed as the hydrogen ion concentration in an acidic solution or in any solution. And we can represent the hydrogen ion concentration in terms of this symbol right here. So how do we measure acidity? Acidity is measured in terms of hydrogen ion concentrations and pH values, where pH values or pH is another form of representing hydrogen ion concentrations, and we'll get to that in further detail later in this video. The relation between hydrogen ion and pH values is the following equation. pH equals to negative natural logarithm of hydrogen ion concentrations within a solution. Now let's understand how we can calculate and understand acidity in terms of hydrogen ion concentrations and pH values. To do this, let's start with a few example questions of how to find hydrogen ion concentrations of solutions themselves and its pH value. In this solution, the concentration of HCl is 0.01 moles per dm cube. We know that hydrochloric acid is a strong acid, therefore it dissociates into 1 mole of hydrogen ions and 1 mole of chloride ions completely. We can find the concentration of hydrogen ions using molar ratios. So, to start, molar ratio, HCl and hydrogen ions have a stoichiometric molar ratio of 1:1. Therefore, we can write that the molar ratio is 1:1. As a result, their concentrations will also have an equal proportion of ratios. Therefore, the hydrogen ion concentration will be the same as the concentration of HCl within the solution. Since we know that the hydrogen ion concentration within the HCl solution is 0.01 moles per dm cube, we can easily find the pH of this solution to be log of 0.01, which is equals to 2. Therefore, the pH of this HCl solution is 2. Let's solve another question. In this question, we have a nitric acid solution of the same concentration as here. Nitric acid is also a strong acid, and therefore it dissociates into H plus and NO3 minus ions. Therefore, according to molar ratio, HNO3 to H plus again has a ratio of 1:1. Therefore, 1:1 in terms of molar ratio. Therefore, the concentrations will also have the same ratios. Therefore, 0.01 will be this one's concentration, and hydrogen ion concentration will also be 0.01, causing the same to happen as that of hydrochloric acid solution. And therefore its pH will also be equals to 2. Now let's find the hydrogen ion concentration and pH of a different kind of acid, where this acid releases 2 hydrogen ions upon dissociation. Here we are discussing H2SO4, sulfuric acid, which is also a strong acid and therefore dissociates completely, but this time it gives us 2 hydrogen ions instead of 1. And now we can also solve this question using molar ratios, where H2SO4 and its hydrogen ions have a molar ratio of 1:2. Therefore, its concentrations will have a ratio similar to this, causing the concentration of sulfuric acid to be 0.01 and its hydrogen ions to have a concentration of 0.02. Therefore, we can rewrite the hydrogen ion concentration and find the pH as minus log 0.02, which is equals to 1.699, which we can round to 1.7. Now that we've learned how to find the hydrogen ion concentration of acidic solutions and their pH values, let's learn how we can compare the hydrogen ion concentrations and the pH values to understand their relative acidities. Using the same examples as before, we have 0.01 mole per dm cube concentration of HCl solution and HNO3 solution. So we know that this has a hydrogen ion concentration of 0.01 mole per dm cube. This as well. They also have equal pH values of 2. Now, what does this tell us? What do we understand? What do we understand when we know that both of them have equal pH values and equal hydrogen ion concentrations? Well, when two solutions have equal pH or hydrogen ion concentration, they have the same acidity. They tend to have the same acidity. Now, how about we compare the hydrogen ion concentrations and pH values of hydrochloric acid and sulfuric acid. Now, here we are at the question where we are going to compare the acidity of hydrochloric acid and sulfuric acid of equal concentrations. Even though these two solutions have equal concentrations, they have different hydrogen ion concentrations and pH values. So, what do we understand when the hydrogen ion concentrations are different and pH values are different? Well, in the case of hydrogen ions. In the case of hydrogen ions, the greater the hydrogen ion concentration, the greater is acidity. And for pH values, the lower the pH value, the greater is acidity. Now, well, this tells us that sulfuric acid has a smaller pH value and a larger hydrogen ion concentration. Therefore, we can conclude that H2SO4 is much more acidic than HCl solution. But where did we understand that when pH is greater or lower compared to another pH, that acidity increases or decreases? Where did we understand that? And how do we understand this inverse relationship between pH and hydrogen ion concentration? And why did we even make the pH value when we can already understand acidity in terms of hydrogen ion concentrations? Well, we can explain all of these in the following example. Here we have two solutions, solution X and solution Y. Solution X has a hydrogen ion concentration of 1.5 times 10 to the power minus 11 moles per dm cube. And solution Y has a hydrogen ion concentration of 6.6 times 10 to the power minus 14. Here we can see that the hydrogen ion concentrations are really odd in the sense that these values are extremely small. These values are extremely small, and it's not that easy for us to compare, because we can obviously say that minus 10 to the power minus 11 is larger than 10 to the power minus 14. However, these values are very hard to manage for us. So we found a way to represent the hydrogen ion concentrations in a simpler format, a format that helps us change these values to a manageable number, where pH value of this solution is 10.8 and pH value of this solution is 13.2. You see, 13.2 is far easier to comprehend than 6.6 times 10 to the power minus 14. And when we start comparing these values, it's much easier to compare 10.8 and 13.2 than 1.5 times 10 to the power minus 11 and 6.6 times 10 to the power minus 14. So to understand pH better, we must first understand and learn about the pH scale. This is the pH scale. The pH scale runs from 0 to 14, where 0 represents the most acidic solution's pH values. Most acidic. And 14 represents most alkaline. And what does the middle number 7 represent? That's in green. It represents neutral solutions. And we must know that any number on the right of 7 represents alkaline solutions, or it has a greater alkalinity. And any number on the left of 7 represents acidic solutions. Now, why is it important to know about pH? in terms of practical use, where there's a practical example. For a farmer who is growing potatoes, he must know the pH of his soil, because potatoes don't grow well in soil that has pHs greater than or lower than 5 or within 5 to 6 range. Potatoes grow best in this range of pH. So if the farmer cannot adjust the pH of his soil properly, he won't have good crops and he won't have good potatoes. And he won't get enough profit at the end of the month when he wants to sell his potatoes, because he won't be able to grow enough. So that's one example of why pH scale is important to know. Now let's solve two example questions so that we can further understand how to solve different questions using pH values and what we can conclude from them. In this question, we've been asked to find pH values in a scenario where to a solution of HCl of 0.25 moles per dm cube of 300 centimeter cube volume, water of 100 centimeter cube is added. First, we have to find the initial pH of the solution and then the final pH of the solution. So to start, let's draw a beaker. In this beaker, there was initially a certain amount of HCl, to which we added some more water. And now they're asking us to find the initial At first, there was 300 centimeter cube of solution of a concentration of 0.25 moles per dm cube. So let's find its initial pH. So step 1, we know that the concentration of HCl is 0.25 moles per dm cube. Therefore, the hydrogen ions also have a concentration of Therefore, the hydrogen ions also have a concentration of 0.25 moles per dm cube. And therefore, since hydrogen ion and HCl have a molar ratio of 1:1, we can write this very easily. Therefore, pH is equals to minus log of 0.25, which is equals to 0.602. Now let's solve the second part of the question, where we have to find the final pH. And to find the final pH, we must understand that initially there was 300 centimeter cube of solution, which had a fixed number of moles of hydrogen ions or hydrochloric acid. Initial moles of hydrochloric acid, which does not change even though I add some more water, causing the whole solution to have a volume of 400 centimeter cubes. So let's start by finding the initial and the constant moles of HCl, which does not change. So we can remove the initial sign, since we know that HCl mole number remains constant. We can find it to be 25 times 300 by 1000, which is, to clarify, concentration into volume by 1000, because this volume is given in centimeter cubes. Therefore, we must convert it to 1000 centimeter cube. Therefore, we must convert it to dm cube. Therefore, the mole comes as 0.075 moles. And the new concentration of HCl must be found. Since more water was added, so concentration is moles by volume is 0.075 by 400 by 1000. We're using the new volume because we're finding the new concentration. The concentration comes to be 0.1876 moles per dm cube. Hydrogen ion concentration will now be 0.1876 mole per dm cube as well. And so pH will be minus log of 0.1876, which is equals to 0.73. This is the new pH value of the final solution. This is the final pH of the solution. In this question, we have been asked again to find the final pH of a resulting solution due to the addition of two different solutions together. But this is a question where we will be considering different types of concepts. First concept is that this is a form of titration reaction, and this is not, or it may be, a neutralization reaction, because we must first find out the final pH. If final pH is equals to 7, we can say that this is a neutralization reaction. However, if it is not 7, then this is not a neutralization reaction. And also, the values to find the hydrogen ion concentration, and the values to find the moles of hydrochloric acid and NaOH have been given. So in questions where they give us the ability to easily find the mole values of different solutions, we must understand that this is usually a limiting reagent or excess reagent type of question. So with these in mind, let's get started with solving this question. So in a beaker, we have added 24 cm cube 0.15 mole per dm cube of HCl, and we have added 20 cm cube 0.1 mole per dm cube of NaOH. Now once they're added, the solution, or the mixture solution, will reach a certain volume level. So this total volume will be 24 plus 20 is 44 cm cube. We can write to be 0.04 dm cube. So first let's find the moles of HCl and moles of NaOH, sodium hydroxide, that was placed in this solution, so that we may understand how much reacted and how much was left unreacted, and which reagent was left unreacted, because this is a limiting reagent type of question. So first, for HCl, we write 0.15 into 24 by 1000 is 3.6 times 10 to the power minus 3 moles. And for NaOH, it is 0.1 times 20 by 1000 into which is equals to 2 times 10 to the power minus 3 moles. Now, moles can be found using concentration and volume as concentration into volume by 1000, just for clarification. Now, let's find out which reagent is in excess. To do that, we must first write the reaction between these two. So NaOH plus HCl reacts in 1:1 ratio to form NaCl salt and 1 mole of water. So we can see that NaOH and HCl react in 1:1 proportions. Therefore, equal amount of moles must react to form product. Whatever is in excess will remain in the solution. So we can see that HCl and NaOH do not react in proportions because there is an excess amount of HCl. So HCl is in excess. So how much of it is in excess? How much of HCl would be left once reaction has been completed? So how much HCl would be left at the end of the reaction? Well, that would be 3.6 minus 2 times 10 to the power minus 3, which would give me 1.6 times 10 to the power minus 3 moles. Now this remaining HCl will contribute to the pH of the remaining solution, because since equal moles of HCl and NaOH reacted, initially because since the products formed are neutral, because NaCl is a neutral salt and H2O is just becomes part of the solvent, HCl that remains will contribute to the pH of the solution, or the acidity of the solution. So HCl will dissociate, the remaining HCl will dissociate as H plus and Cl minus ions. Therefore, to find the H plus ion concentration, we must find the concentration of the HCl that is remaining in the solution after the reaction. To do that, we need the moles, which is 1.6 times 10 to the power minus 3. Now for volume, this time volume will not be 24 centimeter cube. for HCl, because now it's in because the environment within which HCl has changed. It is now in an environment with a volume of 0.04 because now it is in a solution because now it is in an environment of volume 0.044 dm cube. Therefore, we must place 0.044 dm cube at the bottom. This will give us a concentration of 0.036 moles per dm cube. Therefore, pH will be negative log of H plus, which will be equal to the concentration of HCl within the solution, minus log of 0.036, which will be equal to 1.44. This is the end of this video, and I hope you have understood everything that has been explained in this video. But just to recap, in this video, we have understood and learned how to think about acidity in terms of pH, well, this concludes the end of our video, and I hope you have understood everything that was explained. But just to recap, in this video, we learned how to think about acidity in terms of hydrogen ion concentrations and pH values. We learned how to find hydrogen ion concentrations and pH values of different acid solutions in terms of molar ratios. We learned the pH scale. We understood the importance of knowing pH and how to solve questions regarding pH. But what's next? Well, a few questions for the mind. Is pH and strength of an acid correlated? If HCl and HNO3 solutions have the same concentrations and hence same pH, does it mean that they're equally strong? Well, to find out, please watch my next video. Goodbye.